This lesson deals with SPICE parameters for a diode. You can find these notes in the ECE302 ebook in Chapter 10 starting on page 4. Suppose you have a current I1 entering a diode, and we plot the voltage and current of that diode less the resistance of the wires that are here in the contact. We would have a Shockley type equation in the first quadrant, but then in the third quadrant we also have a response as the voltage gets more and more negative. This particular model is the model that's in the PSpice program. The original SPICE program had a discontinuity here, and of course that caused all kinds of problems. We have the following model for this, and that is having a series resistance, which represents the wires themselves and the contact to the piece of silicon material. Then we have a controlled source, which is basically our Shockley equation. Then we have a capacitor in parallel here, which represents the capacitance of the diode, forward or reverse biased. And then a resistor in parallel with that, whose value is 1 over a term called G min, and I'll explain the value of that on the next page. Going around the loop here, the rise in voltage is V1. The drop is I1 times R sub S plus the voltage across the diode, and that's what's being plotted over here. For low frequencies, this is an open circuit. This current I1 is equal to the current of the controlled source plus the current in the resistor 1 over G min. In that first quadrant, we have the Shockley equation. We also have the current that's in that resistor, which would be the voltage times the conductance. Now that's going to be true for the first quadrant, but a little bit into the third quadrant for the PSpice program. Then when we get in the region over here between these two, we're going to have the value of I sub S with a minus 1 because this gets smaller and smaller. We end up getting just a minus 1 times I sub S, but we still have that current in that resistor. Then when you get to this point here, we have the value of I sub BV, which is a negative value. We also have that current in that resistor again. And then when you get in this region over here, we have another Shockley type equation where we've got a new value for I sub S, which is minus I sub BV, and then E raised to the quantity V sub BV plus V sub D with a minus sign over eta BV times V sub T. We have a different value of eta when we're operating over here. This is usually a steeper curve compared to the curve that's in the first quadrant. When the value of V sub D is equal to the breakover voltage, in other words, V sub D is a negative number and this is a positive number, we get 0 here, and you get minus this times e to the 0, which is 1, plus this, which to this point right here. So we do have a continuity in our equations. But these are the equations that are in the PSpice program, but not necessarily in the SPICE program. The capacitance C sub D in the model has a value for your reverse bias, which is our depletion capacitance, and then a value for your forward bias, which is our diffusion capacitance, like we talked about in the last video. In our equations, we have subscripts, we have Greek characters, but in the original SPICE program, they just had uppercase letters. What's the equivalent SPICE notation for the terms that we have in our equations? And also, what are the default values in units? Of course, we've seen I sub S before. That has a default value of 10 femtofarads, and it's just capital I sub capital S, although the PSpice program will also take lowercase letters. The resistor R sub S is noted as RS, has a default value of 0, and of course has units of ohms. Eta, we've seen before, has the symbol N with a default value of 1 and is dimensionless. The term G min is uppercase G min, has a value of 10 to the minus 12th. The reciprocal of that is 10 to the 12th, which is a teraohm. It's a very, very high resistance, but when you put a voltage across this, say 1 volt, you get 1 picoamp of current. When you're in that third quadrant, this is really what you're seeing. This does not exist in the physical diode. This is just part of the modeling. Actually, this is varied sometimes to try to find a convergence point in the PSpice program. Units here for conductance are 1 over ohms. The breakover voltage is referred to as BV in SPICE. Default value is infinite, so you have a perfect diode. And the current at the breakover voltage, we call I sub BV, has a default value of 100 picoamps. We also have this third quadrant exponential for the Zener effect, and that's of course eta sub BV, and then that'd be NBV in SPICE notation with a default value of 1. The term C sub J0 is CJ0, although you can have an O here instead of a 0, and SPICE or PSpice will accept that. The default value is 0, so we have a perfect diode with no capacitance if we want to see what the effect of capacitance is. The term phi0 is VJ, default value of 1 units of volts. M is M, default value of a half. Tau sub T is TT with a default value of 0. Our forward and reverse bias capacitance are set to 0 to see what a perfect diode would do, and this allows you to kind of investigate what happens as terms are changing by just varying one component at a time. As I mentioned, G min is a very, very large resistance when you take its reciprocal. And it's put in there actually for convergence problems because a capacitor is an open circuit for DC, and sometimes that disconnects things in a circuit, and the program has a hard time finding the answer. Suppose you got a DC voltage and a DC current applied to a diode. Well, then we're biasing at a point, and we could have a small signal equivalent circuit. The AC model that we have in the SPICE program is that we have a resistance associated with the wires of the diode, but also the contact between the wire and the P and N material. Those are called ohmic contacts, and we lump that into one resistor. Then we have our controlled source, which we showed had some type of a resistance equation. Then we have a capacitance associated with the diode. Then we have this G-min conductance that's used for convergence. So that's also going to be in our model. Our equivalent is actually what we called R sub D before. It's approximately equal to an open circuit when we're reverse biased, and when we forward bias it is eta V sub T over the current I1 that's coming into the diode. Then the capacitance, C sub AP, or cap, is what we called C sub D previously, and that's we have a reverse bias and a forward bias equation for that capacitance. Now there are many variations of the SPICE program. P-SPICE is one. There's also an LT SPICE, there's a TI SPICE. But these programs usually have built-in models, and I'm showing the model here that's in the P-SPICE evaluation library. It has a lot of the terms we just talked about, but also has some more terms. And the reason for that is that in the original SPICE program, they put two diodes in parallel to model the diode. This gave it a little bit more improvement in terms of the VI characteristics. These are small changes, but they will affect some of the formulas that we've been looking at. I didn't try to go through all the formulas associated with these because that's really a lot more material, and it does have a very minor impact. When you compare it to hand calculations, the model we have is more than adequate. There are some new terms here. The term XTI and EG, which are over here, are actually things we talked about in Chapter 2 for modeling the behavior of I sub S versus temperature. The term IKF, ISR, eta R, which are here, here, and here, are the terms associated with that second diode. It does give you a better modeling of the VI characteristics. And lastly, this term FC here is a term that's used to calculate the transition between the forward bias and reverse bias capacitances. I was using a value of a half here, but you can actually specify it. It's FC times V sub J. So here it would be 0.5 times 0.5. And what we can do is just take this model and test it and see how well things compare to the formulas that we have. They won't be exact, but they'll be close. Let's take a look at that on the next page. Let's take our test circuit from Chapter 2 to do the VI characteristics of a diode. And now let's put in that P-SPICE model for the 1N4148. No matter what model people create or generate, you could use this circuit to test its VI characteristics and see whether it's what you expect to see. I'm going to plot the voltage across the diode and the current through it. I'm also going to refer to these as a device under test, or just DUT for short. Let's take a look at the results. The current through the diode versus the voltage across it, that's node voltage 2. The default here is the swept variable, so you have to change that. You can see that we have kind of an exponential equation, but it almost seems like it's becoming a straight line over here. So as the current's getting higher and higher, we're seeing more and more voltage across the diode. I change the scale here to be logarithmic, so the exponential becomes a straight line. Then you can see here the effect of R sub S. That was that straight line on the previous page. But as the current gets above 10 milliamps, and the drop across that resistor is the current times about a half an ohm. And that becomes bigger and bigger as the current goes up and becomes comparable to the size of the drop across the PN junction. The resistor R sub S is important when the current goes up, but also when the frequency goes up. We have the capacitor in series with this that can create a pole and a zero. So that's important for high frequency results. I also ran the program again, but now sweeping the third quadrant and a little bit of the first quadrant. This was running the case over here with .DC from minus 110 to 10 with 60 millivolts per step. That's about 2,000 data points. And you can see here that the breakdown voltage is around a minus 100 volts, and of course we specified that in the model. Let's take our test circuit from the previous page and let's reverse bias the diode. By making V sub S equal to minus 1 volt, I'm going to ask for the operating point to see what we get for our calculated resistance and capacitance. Get four things out: ID, VD, R equivalent, and cap. Now ID and VD are actually I1 and V1 I defined on page 6. So V1 is the voltage across the diode, anode to cathode, and I1 is the current flowing into this diode. The voltage across the diode is minus 1 volt, and that makes sense because the current flowing in this direction is very small. In fact, it's in nanoamps. It calculated the equivalent resistance as 4 gigaohms. Remember, there's two diodes in parallel. It's actually using the true slope. But with our hand calculation, we'll get a little different answer than this one, but basically a very high resistance. For the capacitance, let's plug in our formula. Now CJ0 is over here, it's 4 pico, and V1 is equal to minus 1, and Phi0 is V sub J, which is equal to a half, and M is 0.333. And I get 2.7734 picofarads, and that's exactly the value I get here. Let's take that same circuit and let's forward bias the diode, putting 5 volts for V sub S. And again, let's ask for the operating point. The voltage across the diode is more like 0.821, and the current is about 41.8 milliamps. Calculates R equivalent as 1.48, and the capacitance is 7.8 nanofarads. Remember, there's two diodes in parallel, and this is the true slope. This does not include the resistor R sub s. Now let's use our equation for just having one diode there, which is eta V sub t over I1. Eta is over here, it's 1.836, and V sub t at room temperature is 25.865 milli. We use a more precise value here. And then the current is 41.8 milliamps, and they get 1.14 ohms. And again, this does not include the resistance R sub s, which is about a half an ohm here. So we have similar numbers, but these will be slightly different because there is another diode in the modeling. For the capacitance, we can calculate this with tau sub t, which is here is 11.54 nano. Our equivalent, let's use this value here of 1.48, and I would predict 7.797 nanofarads, which is exactly the same value here when you round off those last two places. And these are the spice parameters for a diode.